Okay, hello everyone. Welcome again to the part 2 of our Apache TinkerPop 3.8 and 3.7.5 post-release review. So today joined with me again is I'm Yang, and we have Cole, Andrea, and Ken. Okay, all right, let's get started. Let's see, do we have the slides here somewhere? There we go, thank you. Okay, cool. And now the agenda for today. So today we'll be focusing on the breaking changes that went into this release, so that we can talk about some of the stuff that may affect users or as you work on your applications and providers. So so the agenda today is we're going to talk about the strategy changes, the step behavior changes, the runtime changes, and the GLB changes. And next slide, strategy. I'll hand it over to Andrea.
Hi, everyone. I'm going to discuss some of the changes that we've made to strategies in 3.8. And the first one I'm going to talk about is the repeat unroll strategy. So this strategy is an optimization strategy. So it's meant to modify a traversal to be more efficient if possible. And these such strategies should not affect the outcome of a modified traversal, meaning that the pre-optimized should behave the same as the optimized traversal. It's just the optimized one should be a little faster. The repeat unroll strategy converts eligible traversals that contain like a fixed number of repeat loops into an unlooped equivalent, which can be more performant. And these examples show the effect of the strategy on a couple of traversals that use repeat with the times modulator. So for example, the first one repeats out a few times, and it gets converted to explicitly have out.out.out instead of in a loop of 3. And the second example is similar, just that it's using in and has steps. So for 3.7, the strategy would unroll most repeat traversals that have the times modulator, but it was found that the results of the traversal could be affected if you disable the strategy, and especially if the barrier steps were involved. And next slide. So for 3.8, we changed the repeat unroll strategy to be more conservative when checking if a traversal can be automatically unrolled, in order to avoid such situations where we accidentally change the traversal semantics. So now in 3.8, the strategy is only applied if the repeat traversal is only composed of a few limited number of steps that are known to have consistent semantics, whether they're used inside a loop or outside of a loop. The thinking is that the list of eligible steps can be widened in future releases if there is a need, and it's also been verified that these steps will not change when it's used inside of a loop, change behavior of the traversal. So for 3.8, these steps include the vertex and edge steps, like in, out, both, including the V and E alternatives, so out E, in V, etc., and also the other V and the has key value step. And next. Okay, so the next strategy is the standard verification strategy. And this one is just used to kind of validate that the traversal does not have some incorrect usage of some steps. If it's applied and it detects an invalid traversal, it's going to throw a verification exception. So for 3.8, we just added some additional validation to prevent the using cap and inject inside a repeat. And so the cap step reduces the incoming traversers into a single one, so it doesn't make sense to have it in a loop. And the inject step is also not useful in a loop because it will only inject the given arguments into the traversal once, regardless how many loops there are. Okay, and now I'm going to pass it on to Ken to talk about some step changes.
I'm just going to jump in here quickly. Forgot to mention, if you have any questions or comments or thoughts, feel free to drop them down in the comment section or in our Discord events channel. We'll try to address them all at the end.
Great. Could you move to the next slide, please? So to understand some of the changes that were made for 380, we need to explain the concept of eager versus lazy evaluation, a topic that we'll call evaluation ordering. So complete eager evaluation occurs when a step needs to process all of its incoming traversers before it passes on its results to the next step. And then lazy evaluation is when a single traverser goes through all the steps before the next traverser goes through all the steps. So they happen one after another. Most of the time, for most queries, the results are going to be the same. So as a user, you won't notice a difference whether or not the traversal is evaluated eagerly or lazily. There are some exceptions to this, but most of the time, they're going to have the same results. So the example on the slide here sort of shows theoretically what a different output could look like for eager versus lazy, depending on whether or not the sort of group count is a barrier or not. So let's say that group count was a barrier, then you get that top example, which is the eager, where all of the results sort of have the same structure. Whereas if it was lazy, then you get that sort of building up of traversers in the results. So one of the goals of 380 was to make it clear to users how to sort of control the order of evaluation. And that's going to be achieved through using barriers and the lazy step. So barrier would be used for eager and the local step, not the lazy step. The local step would be used for lazy evaluation. And one of the things that you should note, though, is that not the entire traversal needs to be either eager or lazy. Like different parts of the traversal can be evaluated either eagerly or lazily. And but you can sort of fully control this by sort of either nesting locals or like having extra barriers between steps. So why is having control important? And why was that one of the sort of things we wanted to add to 380? I think it's important for users because it makes Gremlin traversals sort of more portable across different providers. And it makes their sort of results for those traversals that could have differences, it makes those more predictable. So if you structure your traversal with like the locals and the barriers in a certain way, it should be provider independent what the results are. Another thing that's probably important is that different evaluation orders will have sort of different performance characteristics. And so you may want to have one or the other depending on what your needs are. If we can move to the next slide. So this is just a diagram to sort of help explain how eager evaluation works. If you notice, the time on this diagram is in the horizontal axis, and each of those T's represents a traverser. So in this, which is eager evaluation, a step processes all the traversers in the stream before it passes on its results to the next step. So if you look at like the vertical section of the G.V, the T1, T2, and T3, which are all different traversers, they all run throughout before they run through count. So in this, most of the time, if you have eager evaluation, you're going to get sort of breadth first style processing. And if we move to the next, and so this diagram is to try to sort of help explain how lazy evaluation works. And time on this side is going to be on the vertical axis. And so in lazy evaluation, a single traverser sort of passes through each step before the next traverser starts. So if you notice how T1 goes through each step, like out, before T2 starts, and so on and so forth. So in many situations, this sort of lazy evaluation leads to depth first style processing. And we could move to the next. So one of the changes we made in 380 was to group count, tree, and subgraph. side effect steps. These were turned into barriers. So a barrier, as a reminder, is just a sort of like a synchronization point that forces all traversers to be processed before that step, which effectively enforces eager evaluation at that point. So that's how you would do that, which is the barrier, which I sort of mentioned earlier. So I also mentioned earlier that there are some traversals that can exhibit a difference in result depending on the evaluation ordering. And this is one of those examples, which is calling the select step on one of these side effects. So the reason for forcing these to become barriers is similar to the reason of giving control to the users, which is by default, when these weren't barriers, a provider could have chosen whether or not to evaluate this lazily or eagerly. And so depending on where the traversal was run, you could get a difference in output. And so by turning all of these into barrier steps, they're all going to be evaluated eagerly by default now. And so you can get more predictable results. But as we sort of will mention later, and we sort of mentioned before, you can always sort of get the lazy evaluation back by wrapping these side effect steps in a local step, something I'll explain in a little bit. So another sort of concept that needs to be explained to sort of better understand some of the 380 changes is local versus global child traversals and how they behave. And I'll probably refer to this as just local versus global semantics. So a traversal parent is a step that can take in a traversal as an argument. So things like repeat, branch, where, those are all examples of traversal parents. The key difference between local and global semantics is how these traversers are passed from the parent to the child. If it's local, then the child can only see a single traverser at a time. So this is sort of demonstrated by that top diagram, where the local child can have access to only one traverser at a time, and the flow goes from the sort of parent to the child as the parent sort of hands the child a single traverser at a time. If it's global, then the child can see all of the traversers, and this is kind of demonstrated by that bottom diagram. So it kind of meant to like reflect an open gate where like depending on whether or not the child traversal is going to be evaluated eagerly or lazily, it can pull as many of the traversers from its parent as it needs. So this is particularly of note, again, if the child traversal contains a barrier step, that global child traversal will be able to, once again, pull all of the traversers from its parents, but a local child could not have done that. And so now that I've explained a bit about local versus global semantics, I'll talk about that step I've mentioned quite a bit previously, which is the local step. So what exactly does local do? Well, local is just a step, a traversal parent whose child has the local semantics that we've sort of just talked about. So you should use the local step whenever you want the child traversal to be run, sort of executed once per traverser. This comes in handy if you don't want barriers to apply to all traversers, because barriers would have naturally waited eagerly and would have pulled all the traversers from previous steps. So again, this only, the local step only guarantees lazy evaluation at that point. But as sort of previously mentioned, a traversal itself can have a mix of lazy and eager evaluation. Local will only at that singular point guarantee sort of lazy evaluation. So let's sort of take a look at examples to see this more clearly. So the top example shows eager evaluation with a barrier, and you'll see like that count step pulls in all of the traversers from out. So that's sort of the eager evaluation at that point. The second example shows how wrapping the count in a local goes back to being lazy evaluation, since each traverser will be affected by count individually solely, which is why you get the 1-1 in the result rather than just the 2. And then the last example sort of demonstrates the local enforced at only a single point, because you can see the output result is 3 and 2, because out itself is a flat map, which means that it can produce more than one traverser, and count will sort of eagerly consume those output traversers, which is why even though you have a local here, it's not completely lazily evaluated. You would need to wrap the count step in yet another sort of local step in order to get that sort of complete lazy evaluation. So one of the changes to 3.8.0 was to the local step, and it now applies per object rather than per traverser. So in the reference implementation of Gremlin, bulking is sort of an optimization that allows a traverser to represent multiple equal objects. And in 3.7, the implementation for local is actually per traverser and not per object. This has been changed to per object in 3.8.0. So the examples on the slide can sort of show you the difference that this makes. So in the top example, if V2 has a bulk of 5, if you had ran that query, you would have seen the output for V1 be 1, and then the output for V2 be immediately jump to 5. This kind of violates what lazy semantics is supposed to do, because it's only supposed to allow a single traverser that represents a single object through at a time, but not a bulked traverser representing multiple objects. So in 3.8.0, you're going to see something like the bottom example where the results will build up one at a time. So the V2 has 1 and then 2 and then 3 and then all the way up till 5. That was sort of clipped out for brevity there, but that will now truly enforce sort of local semantics. So continuing on with this local versus global theme, we have a bit of another topic that requires explaining, which is scoping. So scope in TinkerPop is a bit overloaded and can mean different things depending on the context. For the aggregate step in 3.7, scope local was used to mean local semantics that we've been talking about. But this is the only step that used the term scope in that way. Other steps that use the scope term, they use it to mean whether or not to operate on the entire stream or whether or not to operate on each traverser that is sort of a collection or an iterable. So to simplify the terminology and sort of reduce confusion, aggregate local and its twin store have both been removed. And have both been removed so that scope, the scope parameter sort of means just that, sort of operate on the entire stream or operate on a per traverser that is a collection or iterable. If you want sort of the local aggregate local behavior back, you should just wrap aggregate within a local. But be aware that because of the change to local that was explained on the previous slide, these are not always going to be the exact same depending on whether or not they were bulk traversers. But in most cases, wrapping aggregate and local will be the same as what the old aggregate local had behaved. And so a similar sort of like local global change was made to repeat. So repeat is also a traversal parent, and it will now have global semantics rather than before, which was sort of hybrid local global. That's because the first iteration was local, and then subsequent iterations would be global. So in 3.7, a combination of the repeat unroll strategy that Andrea had talked about earlier and sort of this local versus global could cause confusion to users. So in 3.7, as was explained earlier, repeat unroll strategy was enabled for like most traversals that had repeat. And so a lot of users kind of thought that was just a natural way that repeat worked. But the problem is that's not actually the semantics for repeat. Repeat is supposed to apply the same traversal sort of multiple times per traverser. So that leads to that sort of mix of local and global semantics that I was talking about, where in the initial iteration, it'll be local. And then as the traversers from the initial iteration loop back to the front of the repeat, you're going to see sort of almost global semantics because the repeat traversal then can have access to more than a single traverser. So to make things simpler, repeat has been changed to just always be global by default, as that was sort of the kind of semantic that some users seem to expect. If you want the old sort of repeat style, again, wrap the repeat inside a local step, and you should see the same behavior for most repeat traversals. There are some differences like dedupe, dedupe is like one of those special cases that was supposed to act globally within repeat, but the local will sort of reset the dedupe. So there are some minor differences, but in most cases, wrapping a repeat inside a local will give you back that same behavior as before. I'll hand it back to Andrea now to talk about range-based steps.
Okay, so for the next couple of slides, range, limit, skip, and tail are what I refer to as like range-based steps because they filter traversers given a low to high range. So limit has an implicit low range of 0, and skip has an implicit high of -1 or like unlimited, and tail has an implicit high of the number of traversers. So in 3.7, these steps were not really useful when used inside a repeat loop because their states were persisted between loops. And because of that, sometimes traversers were unexpectedly filtered if the repeat unroll strategy did not automatically convert the traversal into an unlooped traversal. So for this example, which assumes that the Grateful Dead sample graph has been preloaded, it shows how attempting to do like a limited walk along the graph using the limit step, it doesn't actually produce any results because the limit of 2 is reached in the first loop. And then after in subsequent loops, all of the traversers are filtered because it was already reached in the first loop. Slide. So for 3.8, the range, limit, skip, and tail have been changed so that the ranges are applied per iteration. So if you continue with the previous example with the limited walk along the Grateful Dead graph, it actually produces 2 results now because the limit of a 2 is applied per loop. Okay. And continuing again with the same steps, the range-based steps, the previous slides were dealing with the default or the global scope. So the next couple are addressing changes when the steps are used with the local scope instead of global or default. So in 3.7, when the range, limit, skip, and tail were used with the local scope, anytime there was a resulting single item collection, it would be automatically unfolded. And instead of returning the collection, it would return that single object. So for traversals where the users know that exactly one result is returned is not really a problem, but it becomes problematic when traversals could return a variable number of results. And because this added complexity where the user would have to check, did it return a collection or did it return the single item in order to continue processing the result? So this limit example shows how the result sizes can be kind of unpredictable depending on how many nodes in the graph have the my property. And just because specifying a limit of 10, that doesn't guarantee you're going to get 10 results. You might get none if there's no nodes with that property, or you might get one if there's one node with that property. And in 3.7, that one node collection will be automatically unfolded, and then you're going to get the single result instead of the collection. And the next slide. So in 3.8, we changed these steps to when they're used with local scope, it's always going to return a collection, no matter how many items are in it. So single item collection no longer going to be automatically unfolded. And so the first two examples shows how you're always going to get a collection, no matter how many items are inside. And the last one shows if you still want to only return like the single item instead of a collection, you can just put an unfold step at the end of the traversal, and you'll get the previous behavior. Okay, next step, we're moving on to split, which is a step that's used to split strings based on a given separator. And in 3.8, we added the ability to split a string into its characters if the separator is an empty string. So in 3.7, if you specify an empty separator, the string is basically not modified. But in 3.8, it will then split that string into its characters. So hello will become HELLO. Okay, now I'll pass it on to Cole to talk about none and discard.
All right, thanks, Andrea. Yeah, so there's a couple of steps I want to highlight here. And the first one is none and discard. So for those of you who don't know, as of 3.7, we actually had two different none steps. There's the none step that's been around for a long time, which is the no argument none step. And this step was used to drop all of the traversers in the stream. It's a bit of a niche step. It was mostly used to enable the iterate terminal step. Maybe had some occasional uses in a choose case or something like that, but it was mostly a niche step. And in 3.7, we introduced the none predicate step, and this was connected to the any p and all p as well. And those three steps will filter lists based on if all, none, or any of the elements match the provided predicate. So this was a little bit confusing just because they were completely unrelated steps that shared a name. And to resolve this, the no argument none step has now been changed to discard because it discards all of the traversals it sees. So this renaming was just to disambiguate the steps a bit more, make it more clear. And the none name is better used for the none predicate step. It fits better with its related steps as well. So that's just a small change to help improve the consistency there. Jump to the next slide. I want to take a look at choose. So the choose step, the examples I've got here are kind of in the what I call the switch form of choose. And there's a few changes that were made here to make it a little bit more intuitive, a bit easier to use. So the first example I've got on the left here is that the choose now only takes the first matching option. So choose used to always jump to, it would run all options that match the provided traverser, but now it's just the first one. So if we take a look at that example, this is just in the modern graph. The Marco vertex would match the first two options here because the age is exactly 29, which is also less than 30. But if you see in the output, you can see that Marco vertex only went down the path of the option 29, the first option. It no longer matches both. One other thing I want to point out in that output is all of the vertices that don't match either of those options just get passed through unmodified. The other change I want to highlight is with pick none and pick dot unproductive. I tend to think of these as the equivalent of a default case in a switch statement in a normal programming language. The reason we have two of them is we sort of have two different types of default in TinkerPop. So in the example here, it's the same query, but I've added two more options on it. But if we look at the choose itself, the choose traversal is values age. So that will try and extract the age property from the provided vertices. And there's sort of two base cases we can land into is that the vertex can have an age, but it doesn't match any of our provided cases. And that goes to the pick.none case because none of them match. But there's also the option of the vertex has no age property, so that choose traversal is unproductive. So that's a different type of default case, and that's where this pick unproductive comes in, which is new syntax in 3.8. So just look at the results there. Marco and Vada still match their original two options. And then you can see that both Josh and Peter both follow that into that none path as they have ages, but they're not matching any of the previous cases. And Lop and Ripple are both unproductive because they are software nodes in the graph. They don't have ages. So the goal here is just make this work a little bit more like a switch statement or an if-else chain that programmers from other languages might be more familiar with, and just make it a bit more intuitive and easy to use. Jumping over to the next slide. I wanted to look at some cases of width modulation, and this is really just a bit of an implementation detail and a bug fix, but the way the steps listed on screen here used to be implemented, they would store a lot of their internal state in the same parameters object that was used for width modulation, and it meant that the width modulator could unintentionally alter the internal state of these steps. The simplest example to explain is for add v and add e. When you add a property for those steps, just with the property step, that would get stored in the same parameters object used for width modulation. And that meant that the width modulator could also add properties to these steps, which was never a documented behavior, never intended. So for all these steps, it's been cleaned up in 3.8 where the width modulation state is completely independent from the other state of the steps, and they can't have any crossover or weird interactions there. Jumping over to the next slide, there's also some changes to bimodulation. Once again, looking at all the steps on screen here, these are all steps that can take a bimodulator, but don't make sense to take multiple bimodulators. They really only are meaningful with a single modulator. And previously, you could attach as many of them as you wanted to the step, and it would lead to strange and unexpected results, and it wasn't necessarily consistent. So now there's just an exception that gets thrown if you try and put multiple bimodulators on these steps, just to let the user know that this is probably not the traversal they intend to write. It's probably not going to work the way they want, and it will direct them to just use a single bimodulator and get more correct results. Moving on to the next slide. Yeah, the merge v and merge e. There's some changes we've made here to the mid-traversal forms of these steps, which is that they now pass the created or matched element into the option traversals. So previously, what would happen in the mid-traversal form of these steps is that the option traversals would be seeded with the elements that initially flowed into the merge step. So in that first example there, you can see our merge step, we're matching the Josh vertex in the modern graph. But the start of that traversal is a g.v1, which is producing the Marco vertex. And you'll see is in the results there, the onMatch query is just extracting the name and forcing it to uppercase. But what the result of this is that we're actually overwriting the name of the Josh vertex with all caps Marco because it's grabbing the element from that originally flowed into merge v, not the matched element. This is something that found a lot of users got confused with and wasn't expected. And it's also inconsistent with the start step versions of merge v and merge e. So if those steps are the first step of the traversal, the options are always seeded with the matched element or the matched or created element, not whatever flowed into it, because nothing flows into it as a start step. So you can just see in the 380 example here now, the on-matched traversal is always seeded with the matched element. So finally get the name of Josh at the end. So this is really the behavior that we found users seem to expect. It seems to be more intuitive. So that's all been corrected to be all aligned now. And with that, I'll pass off to Yang to talk about some GLV changes.
Yeah, okay, cool. Thank you, Cole. So I'm actually going to talk about the GLV changes regarding serializers first instead of the runtime. So one thing that's changing for sake of consistency is actually what we changed to how properties and elements are deserialized as they are returned. So previously, GLVs did different things depending on their serializers, some and their languages. Some deserialize into nones for null or empty properties, or some deserialize into empty lists. And sometimes they would deserialize into native objects like JavaScript. So now with 3.8, we've made them consistent. So all the properties, element properties, they will be deserialized into a list of the property object if there are actual properties, or empty lists for missing ones. So this change actually in particular applies rather breaking ones to Python, .NET, and JavaScript. So in Python and .NET, specifically in GraphZone, they will no longer deserialize the missing properties into none or null. They will just be empty lists. In JavaScript, the change is a bit more extensive. So basically, all properties are now deserialized into list of properties or vertex objects. Vertex property objects, sorry. And then they will no longer return JavaScript objects. So for users that is processing these properties after their return, that is something to take notice. And again, also, if it's empty, then it will be an empty list or array. Yeah. So, and last but not least, there are some, as usual, runtime changes that comes with this major upgrade. One major thing in Java is that we have now officially removed Java 8 support, and the supported versions are now 11 and 17. So, we've seen the community that's asking for, more modern versions of Java in the project. While that it's kind of a long-term goal, obviously, to stay in the future, to stay on top of the Java releases, but there's been some difficulties along with how, our Groovy supports and various legacy code that's still in there. So I think a step towards that is to get Java 8 support removed. So that's what we have here. And again, for the other GLVs, for JavaScript, we still have Node 20 support, but now we have Node 22 and 24 support added. And for Go, it's upgraded to 1.25, and Python, it's to 3.10. And with that, I think that is everything for today. Yeah, many thanks to everyone who have contributed to this release. Many thanks for the awesome work. For a comprehensive list of changes, please see the changelog. Yes, as also shown in the QR code. If you scan that, that should take you to the website that's listed down below. And now, any questions regarding this? And do note if you have questions along the way, like after the stream or anything, feel free to drop them in the Discord, in the users group, in the dev list, or yeah. I mean, I think 3.8 was, given it's a pretty big release in terms of semantics and new steps. I think we're looking forward to the feedback. I'm sure there will be weird cases or edge cases or bugs that comes because this is a 3.8.0 release. So yeah, I'd also be curious. Sorry, Cole, go ahead.
So yeah, overall, I'm really excited about the release. There's a lot of kind of nitty gritty details, especially the ones we talked about today. But I think we were able to look at a lot of long-standing kind of complaints and inconsistencies and points of confusion in the Gremlin language, and it was really great to be able to kind of take a look at all those and try and work them all out here. So I'm really excited to get feedback on this release. I think it's a great step for the Gremlin language overall.
Yeah, and also a quick shout out to the dev list. If you've been following, there has been quite a bit of discussions and proposals going on. So please check them out and then give your input, especially for our future release versions, such as the 4.0, which will have another set of awesome and exciting features. So yeah. If there's I don't see any questions here. So yeah, so feel free to drop them into our Discord or the mailing lists. So with that, I guess I'll wrap it up. Thank you, everyone. See you next time.
Thanks so much. Bye.
Gremlin out.